Okay, welcome back to the channel. In this video, we will be working question 4 of the 2012 past paper, Chemistry, Unit 2. So in this question, for part A, we are given an alkene, right? So the first question is, give the structural formula for the reaction of compound A, the alkene with aqueous bromine, liquid bromine, cold potassium permanganate, and hot potassium permanganate. So we're going to do the one with bromine first, aqueous bromine. So if we react an alkene with aqueous bromine, once it's aqueous bromine, we know that the double bond, it will break, right? Let me put this hydrogen up here. So we know that the double bond will break, and you will get a bromohydrogen, right? So if you react compound A with aqueous bromine, bromine atom will go to one carbon, and the hydroxyl group will go to the next carbon. So the first one, this is the structure for compound A with aqueous bromine. If it was liquid bromine, then that point, the double bond, when it breaks, you will add 2 atoms of bromine. So if it's liquid bromine, you will get 2 bromine atoms. But with aqueous bromine, you dissolve the bromine in water. So that is why you get Br and OH. So when it's aqueous, Br and OH. For the liquid, you will get 2 Br atoms. Alright? So that's it for the one with aqueous and liquid bromine. Alright? When it comes to potassium permanganate now, if it is cold potassium permanganate, so cold KMnO4, right? You will simply just break the double bond, right? And you will get 2 OH groups on it. Alright? So you get a diol, 2 OH groups. So if it's cold potassium permanganate, the alkene is oxidized to an alcohol, but it must be 2 OH groups, so it's a diol. So that's straightforward. So all they're asking for is the structure of compound A when it reacts with each of these reagents. So this is the structure when compound A reacts with cold potassium permanganate. Now, if it reacts with hot potassium permanganate, so when it reacts with hot potassium permanganate, it's a little different. So first, you locate the carbon to carbon double bond, right? And you cleave it. So the bond is going to break, alright? So what you're going to do now, this carbon, each carbon of the double bond, so you're going to get this ketone group, alright? Or the carbonyl group, C double bond O, alright? And you put back everything else. So this is one product. Now, based on the structure of the alkene, you might get an aldehyde, you might get a ketone, you might get carbon dioxide and water. If the carbon of the double bond has two hydrogens, right, you will get carbon dioxide and water. It would have been oxidized to methanoic acid, but that will be further broken down into carbon dioxide and water. So if the carbon of the double bond has two hydrogens, you are going to get CO2 and water. So this is one product, and you will get carbon dioxide and water from this part. Alright, so with the alkene, if it's hot potassium permanganate, it is going to be oxidized, right? What you get is based on the structure. If you have two alkyl groups, or in this case two methyl groups attached to the carbon, then you get a ketone. So this is the structure for a ketone. So when two methyl groups are attached, you will get a ketone. Alright? If you have two hydrogens attached, you will get CO2 and water. So for this one, you will get a ketone and carbon dioxide and water when you react it with hot potassium permanganate. So these are the answers. Alright, let me just this. So you would have gotten methanoic acid, and then it would have been broken down into CO2 and water. As a little side note, if this was a CH3 group, right? So if it was two hydrogens, you get carbon dioxide and water. But if you have a hydrogen and an alkyl group, then this is what would have happened. You get the carbon, right? Double bond O. It has a hydrogen and it has a CH3 group. Now this would be an aldehyde. So C, double bond O, H, C, that's the functional group for the aldehyde. If you get an aldehyde, it will be further oxidized to a carboxylic acid. Alright? Let me write it. So C, double bond O. So that's the aldehyde, and it will be further oxidized to a carboxylic acid. So, two methyl groups, you get a ketone. Alright? And it stops at the ketone. If you get the aldehyde, it will be further oxidized to the carboxylic acid. All you are doing for the carboxylic acid, the only difference between the aldehyde, so aldehyde, the only difference, you have an OH bond instead of the H. So this is the carboxylic acid. Alright? So aldehyde will always be oxidized to the carboxylic acid, and it stops right there. If you get a ketone, that's it. If it's an aldehyde, it goes to the carboxylic acid. So two carbons attached to this carbon of the double bond, you get a ketone. If it's a hydrogen, and a CH3 group, you get the aldehyde. But if it's two hydrogen, that's when you get the carbon dioxide and water. So that's it for this question. So again, the answer, it would have been this, the ketone, carbon dioxide and water. Alright, so part B now of the question is asking if compound A will exhibit geometric isomerism. So remember, with geometric isomerism, the carbons of the double bond, right? Each of them must have a group in common. So, for example, each of them must have a hydrogen, right? The reason for that is with cis, the same groups must be on the same side, right? So let's say I have CH3 and fluorine, right? All the groups don't have to be the same. But for you to get cis strands, each carbon of the double bond must have a group in common. So for example, both of them have a hydrogen. The reason why this is important, in one instance, both atoms will be on the same side. That would give you cis. And then in the next instance, they will be on opposite sides of the double bond. Alright? So with cis, though the same group is on the same side of the double bond, and in trans, they are on opposite sides of the double bond. So trans and cis. Now if you look at this compound, alright, so we have carbon, carbon to carbon double bond. We have CH3 group there. So that's the structure for compound A. Remember, for it to be cis and trans, right, each carbon atom must have a group in common. If you look, the two carbon atoms, right, this one have two hydrogens, this one have two methyl groups. They don't have any group in common. So if they don't have any group in common, then we cannot have two of the same groups being on the same side and then being on the opposite side. So this cannot exhibit geometric isomerism. For it to be geometric, both of these CH3 groups would have to be on the same side. So each carbon would have to have the same group. Alright? So like each of them have a CH3 group, or each of them have a hydrogen atom. So in that case, we could get them being on the same side and then being on opposite sides. But I cannot have this when the same groups are attached to one carbon of the double bond. So if you look, this is cis and trans because both carbon atoms have a group in common. In this case, it's hydrogen. So we can have the hydrogen on both sides or on opposite sides. So you get cis trans. But in this case, each carbon atom have the same groups attached. Alright, so this one have two hydrogens. So for the answer, it does not exhibit geometric isomerism. So that's a no, it does not exhibit geometric isomerism. And the reason for that, you can see that the groups that are the same is attached to one carbon atom of the double bond. So the groups that are the same, right? In bracket you can put H is attached to this same carbon atom. Of the double bond. Alright, and the second reason, so because they are attached to the same carbon atoms, then you cannot get them in the cis or trans configuration. So we have the two groups that are the same, right? Attached to the same carbon atom of the double bond. So because of that, the groups that are the same cannot appear on the same side. Right? Hence, no cis or trans configuration. Alright, so that's it. Both groups that are the same, so the two hydrogens are attached to the same carbon, and for that reason, you cannot get the cis or trans configuration, because this cannot be here. Alright, so that's it for part B. Alright, so part B of the question is asking for the mechanism for the addition of HBr to the compound A. So HBr. So the Br molecule is polarized, bromine is electronegative, hydrogen is not. So the hydrogen will have a slightly positive charge, the bromine will have a slightly negative charge, right? So when the bromine and the HBr molecule approaches the double bond, remember the double bond, it will have a lone pair because of the pi electrons, right? So in a double bond you have p orbitals that overlap to form a pi bond, and in it you have a lone pair of electrons. So that makes it a nucleophile. Any compound, anything with a lone pair of electrons can act as a nucleophile. This is a slightly positive charge, it's an electrophile. So the pi bond will do a nucleophilic attack on the HBr molecule. It's a curved arrow because the pi bond is donating 2 electrons, so use a curved arrow. Once the bond is polarized, it's going to break heterolytically, so the bromine atom gets the 2 electrons from the bond. So again, we use a curved arrow. Ensure that the arrow is pointing from the source of the electron to where it is going. So the electrons here are coming from the bond to the bromine atom. So this bond is broken heterolytically. And so now the hydrogen is bonded to the carbon. Hold on. Now, when you're adding a hydrogen halide to an alkene, so these two carbons are the carbons of the double bond. But this one have more hydrogen, right? So that is where you will put the hydrogen. Alright, so when you're adding hydrogen halide, the carbon of the double bond that has more hydrogen, that's the one that will get the hydrogen of the hydrogen halide. That's Markovnikov's rule. Right, so, that's the product. So in the first step, a carbocation is formed, right, from the nucleophilic attack on the HBr molecule by the pi electrons. So you always tell what is happening in the mechanism. Just a short statement. So you have a nucleophilic attack on the HBr molecule by pi electrons, resulting in the formation of a carbocation. So that is step 1. And then in step 2, remember this bond was broken, so you will get Br minus. Alright, so let's draw back now the carbocation. And then we will have a nucleophilic attack on the carbocation by the bromide ion. Right. So it's a nucleophilic attack on the carbocation. So that's it. The video for this in detailed explanation, right, is on the channel already. So you can just look for electrophilic addition of alkenes. Alright, so this is it. Nucleophilic attack on the HBr molecule, resulting in the formation of the carbocation, and then you will have nucleophilic attack on the carbocation by the bromide ion, and that is how you get your haloalkane. Now the final question was asking what is the name for this mechanism. So alkenes do the reaction of alkenes. The mechanism is electrophilic addition. Right, so remember the alkene is a nucleophile because of the double bond. Alright? So it will attack electrophiles. So it is electrophilic addition. It's not substitution because we are not substituting anything. We are just adding. Right? So it is electrophilic addition. So that's the question. That's the end of this question. If you have any question, you can ask in the comment section. You can subscribe and click the notification bell, so once I upload a question or anything else, you will be notified.